In this video, we're going to see how to use u-Substitution to evaluate definite integrals. And first off, a little reminder of what u-Substitution is. So u-Substitution is basically used when we see a composite function where the derivative of the inner function is multiplied in some way, and I'll talk about that shortly, to the rest. It is basically used to undo, so it undoes chain rule. And this is really the second type of integral that I'll always sort of consider. So the first type of integral is something like this, where I have the antiderivative of sine of x dx. This does not require u-Substitution because I know the antiderivative of sine is negative cosine x. So I don't need u-Substitution. However, what if I gave something like this? The antiderivative of x squared sine of x cubed dx. And I'm not going to go into the details here, we'll see some examples, but this is a case where we would use u-Substitution. I'm going to actually end up letting u equal this inner function, x cubed. I'm going to see that the derivative of u with respect to x is 3x squared. And what's going to actually happen is, when I replace this dx with the du by solving this through, I'll get that dx is du over 3x squared, and the x squareds are going to cancel. That's why I said it's just sort of, I don't need the 3 here, the constant can come out, but I need those variables to cancel. Let's see a couple of examples. There are 2 ways to do this. So the first way is just based on what we saw in a video a few weeks ago about u-Substitution, where I'm going to just consider this, and I'm going to just try to find the antiderivative, then come back. So I'm going to just look at the antiderivative of tangent alpha d alpha. And in order to solve this or evaluate this, I'm going to rewrite tangent as sine of alpha over cosine of alpha d alpha. And now, if I, let me change colors, I'm going to be switching into u's now, let u equal cosine of alpha, this will work because it's multiplied up top by a sine alpha that will eventually cancel. So du d alpha equals negative sine alpha, and when I solve this off, that lets me know that d alpha, by multiplying by d alpha and dividing by negative sine, will equal du divided by negative sine alpha. And so I can take this and rewrite it as the antiderivative. I'm going to leave the sine alpha here briefly, change the cosine alpha into u, but then change the d alpha, because I wanted this all in terms of u's, into this du over negative sine of alpha. The sines cancel. The negative can come out front, and I'll have the negative antiderivative of 1 over u du, which we know is negative natural log of the absolute value of u plus c. But u was cosine alpha, so this will be negative natural log of the absolute value of cosine of alpha plus c. And then if I'm doing this method, this is not the method I actually recommend, I changed back into alphas, and so now I can just evaluate the negative natural log of the absolute value of cosine of alpha from negative pi over 4 to pi over 3. The cosine of pi over 3 is 1/2. The cosine of negative pi over 4, so I have minus a negative natural log of root 2 over 2. And as a teacher, I guess I'm okay with this. This would be plus at the end of the day here. But it's worth knowing for something like the AP test, they can fix this form a little bit. So this is really negative natural log of 2 to the negative first. And recall that root 2 over 2 is the same thing as 1 over root 2, which means this is really plus the natural log of 2 to the negative 1/2. And through all of this, I can use my logarithm properties and bring out this negative and get the natural log of 2, and bring this out, minus 1/2 natural log of 2, which gives me the natural log of 2 all divided by 2. Alright, so this is not the way I like to do it. I don't like to change from alphas to u's and then u's back into alphas. I like a little bit of a cleaner way to do this. So the problem is when I change to u's, these are not u values. In this problem, these are t values. So I'm going to do the same basic thing. I'm going to let u equal this 2t minus 3. And that's going to work because the derivative of this is just 2, so I don't have to cancel out any variable out here. So du dt is 2, which means dt equals du over 2. But here's the problem. When I write this integral of the square root of u times du over 2, these were t values to begin with, so I need to change them into u values. But it's not that hard. So when t is equal to 2, that means u is equal to 2 times 2 minus 3, which is 1. So my lower limit here is 1. And when t is equal to 14, u is equal to 2 times 14 minus 3, which is 25. So my upper limit's 25. So I just use this let statement that relates u's to t's, in this case, to change my t values into u values, and now I'm never going to go back. I'm just going to deal with all this in terms of u. So I'll bring the 2 out as a 1/2. It's a constant. I have the integral from 1 to 25. I'm going to treat this square root of u as u to the 1/2 power. And now the antiderivative of u to the 1/2 power is going to be 2/3 u to the 3/2. And I still have this 1/2 times it, evaluated from 1 to 25. 1/2 times 2/3 is 1/3. So let me do that. So that's going to be 1/3. So I'll have 1/3 times 25 to the 3/2 minus 1/3 times 1 to the 3/2. 25 to 3/2, the square root of 25 is 5. 5 cubed is 125, so that's going to be 125 over 3. The square root of 1 is 1. 1 cubed is 1, so it's going to be minus 1 over 3. That gives me 124 over 3, and this is not divisible by 3. Therefore, this is completely reduced. Feel free to comment below if you do have any questions, and I hope this helped you out.